Hello everyone, welcome to my channel. This is an educational channel where we take deep dives into some great but lesser known theories of everything. And today is our 432nd video on the reciprocal system of theory of Dewey B. Larson. In 1959, Mr. Larson came out with his two fundamental postulates about how he believed that the universe operated. And then he took those two postulates and through a process of deduction, he arrived at a theoretical universe about, what the universe would look like if his postulates were correct. And then in some of his books, he compared his theoretical universe with the measured universe of the legacy scientists, and that they had compiled through experiments in their laboratories and observatories. And we're looking at the results of one of those books. It's called Basic Properties of Matter. It's on chemistry, and we're in chapter 4 called Compressibility. This is about how you compress, when you compress a solid, how much does it compress, compared one compared to another, compare aluminum with gold, how much do they compress at, 100 atmospheres or something like that. All right, well, so that's what we're going to get into, just some background on the reciprocal system. Larson calls it the reciprocal system. He also calls it the universe of motion. His two fundamental postulates focus on motion. The first one, which is by far more important, says that the universe is composed entirely of one component, motion, existing in 3 dimensions, in discrete units, and with 2 reciprocal aspects, space and time. And then the second postulate is that the universe conforms to the relations of ordinary commutative mathematics. Its primary magnitudes are absolute, and its geometry is Euclidean. I, among others, would dispute that second postulate and say that it's not inclusive enough, and also even say that Larson's own illustrations demonstrate how his second postulate is incorrect, or at least limited, where he goes for the Euclidean geometry, but at the same time claims that his Euclidean geometry is not capable of representing everything. We can get into that through looking at the first postulate, which is, his universe of motion. Now, when he talks about motion, he's really referring to what he calls a scalar motion. Not our normal conception of motion that has a direction, but a scalar motion has no direction or no specific direction. It just has really in or out. You can envision this using a balloon that you put dots on. As you blow up the balloon, all the dots will be moving away from each other. As you contract the balloon, all the dots will be moving toward each other. But in both cases, none of the dots will be moving in any specific direction. Each one will be moving away from each other one. And you can't, assign any type of direction. Not until you actually decide upon a reference point. Arbitrarily, you can say, this particular dot is motionless. And then you can start imputing direction. So the directions are not the result of the motion. They are the result of the reference system. Okay, so we've got a universe made out of scalar motion. And motion is the relationship between space and time. Space and time are the two reciprocal aspects of motion. Basically, all motion is a fraction, with space or time as the numerator and time or space as the denominator. The most basic kind of motion that we know of is speed. And, the bicycle's going 15 miles per hour. 15 miles of space and 1 hour of time. Space over time is speed. So, and if you decide to double the speed, you can say now the bike is going 30 miles per hour. Or equivalently, you can say now the bike is going 15 miles per half hour. You can either double the speed, double the space, or you can halve the time. That is a reciprocal relationship. So at least as far as the most basic motion that we know of, it does have a reciprocal relationship between space and time. But Larson generalizes that and applies it to all motions, which he says are really all of our scientific phenomena, including mass, energy, magnetism, electricity, pressure, power, momentum, acceleration. These are all fractions in Larson's system, with space or time as the numerator and time or space as the denominator. But space and time, as it also says in his first postulate, that space, time, and motion come in 3 dimensions. So you can have multiple dimensions of your numerator or denominator or both when you reckon by space-time fractions. And this is a great system because unlike the MKS system, which has 3 variables, matter, kilograms, meter, kilograms, seconds, you get rid of the kilograms. The kilograms, part of mass, matter, so they are time to the 3rd power or space to the 3rd power. So you can substitute that out, and now you're only dealing with 2 variables, which is much less messy to deal with. Okay, so you got this scalar motion, but the scalar motion can be basically abstracted or stopped by assigning a reference point as motionless. When you do that, you end up with what you could call a spatial reference system, but in some cases you could get a temporal reference system, a reference system in space or in time. The reference system in space looks like coordinate space, that is Euclidean geometry, XYZ coordinates, 3 dimensions of space in a still frame. And we are accustomed to that idea. We see ourselves generally as moving through a 3-dimensional frame of space. And we see events unfolding in time. And so time is always getting later and later and later. And time is moving in no specific direction. So what we really are seeing there is we see a 3-dimensional vectorial space, and we see a 1-dimensional scalar motion in time. Now, if we, okay, we'll just leave it there. Now, the other and very important prong of Larson's first postulate is the discrete unit postulate. Space, time, and motion come only in discrete units. You have to have a full unit of space in order to have space. Same with time, same with motion. If you don't have a full unit, then you don't have anything. It's just like, I went to the apple tree and I picked half an apple. That's absurd. You can't do that. It's either one or none. You can't say, most important day of my life yesterday, I had a baby. I had half a baby. No, you can't say that. You have to say it's either one full baby or 2 or 3, but not 1/2, not 1/5, not 0.26. there's things in the universe that are quantized. You have to have a whole unit. And so that is true here with space, time, and motion. Now, the unit of space is very, very small, and the unit of time is even smaller. So, you know, you have a kind of a low bar to get up to a full unit, but there are many situations where you don't, and we'll look at that. But what this basically means is if you have one full unit of space in one full unit of time, space over time being speed, you have what Larson calls unit speed. And unit speed, 1 over 1 equals 1. Unit speed in Larson's system is the speed of light. So that's really what you have as the empty universe, the universe that you have when you don't have anything in the universe of motion. Anytime if you have a universe of motion, motion precedes everything else. So you have to be able to conceive of motion without anything moving. And Larson's empty universe, or his null point, neutral point, ether, origin, what he calls the progression of the natural reference system, is motion outward at the speed of light in all directions. This is the source. This is you know, Buckminster Fuller would have called it the isotropic vector matrix. It's a scalar motion outward. Now, again, we talked about this coordinate space, 3 dimensions of space, but it requires 3 dimensions of space just to describe 1 dimension of time. So this, 1 dimension of motion, sorry. So you need 3 dimensions of scalar motion, but you really only can express 1 at a time with Euclidean geometry, or even with polar Euclidean geometry. So that shows that the Euclidean geometry is not the full picture, not going to give you the full picture, and should have been replaced by Larson by some more inclusive kind of geometry. But he didn't really want to do that because these 20th century geometries are, you know, another obstacle of comprehension. So he stuck with the well-known Euclidean geometry, but that only goes so far. Now, when you're talking about scalar motion, Euclidean geometry is off the table, and not even mentioning, you know, well, you're getting into the 3 dimensions of scalar motion. So that is what you have when you have an empty universe, is you have outward motion at the speed of light in all directions. And then matter, or anything, is created by kind of rolling back that source, that outward motion, and gradually turning it into a inward motion. Larson calls that outward motion of that expanding balloon, calls it the progression, and the inward motion is analogous to gravitation. So you, through rotating, or, you know, other theorists have, you know, kind of called it tying knots. You're really tying knots in the outward motion to turn it into inward motion, but you have to do it in 3 dimensions. So that's why when Larson has his periodic table, he uses 3 numbers on his periodic table for each element. The first is 2-dimensional rotation. The second is a secondary 2-dimensional rotation. That's because there are 2 photons at the core of matter for him. So each one of them have to be rotated in 2 dimensions, and then there is a 3rd dimension. Now, my understanding of that may not be correct as far as the why you have to have 2 2-dimensional rotations. You need 2-dimensional rotations to get 3 dimensions. I know that. I'm not exactly sure how the two photons fit. I think I could probably refresh my memory and get it, but right now I'm a little out of it as far as that goes. Anyway, that's really how you get matter for Larson. But this empty universe moving outward at the speed of light in all directions is the center point. So you have, on one half, you have the material sector. That is the sector that's moving slower than the speed of light. And that's the sector that we're familiar and accustomed to dealing with its coordinate space and clock time, the scalar motion of time, or the progression or the flow of time. But then there's what he calls the cosmic sector of the universe that is moving faster than the speed of light. And this is a whole sector of the universe that we really know nothing about, or mainstream science knows nothing about, which is the realm of coordinate time, 3 dimensions of time, and clock space. The space is still progressing. So the temporal reference system is really this kind of, maybe you would call it polar Euclidean geometry, and a scalar motion in time. So in space, a polar Euclidean geometry in time, and scalar motion, 1 dimension in space. And you can see the reciprocal relationship between them. So when you cross that unit speed boundary, you have to change the rules, and the time and space rules are interchanged. Now, within each one of those two sectors, there is also a mini sector, or an inside sector, that has to do with, again, the discrete unit postulate. You have to have a full unit of space in the material sector, and in the cosmic sector, you have to have a full unit of time. Now, you don't have that in certain atomic and molecular interactions, where they are within 1 unit of space. And so if you don't have a full unit of space, then you don't have space. And if you don't have space, then you only have time, because the universe is made out of space and time. And so Larson calls this the time region. This is the region of atomic and molecular interactions. And so, but you also have to, once you cross that unit speed boundary, the rules reverse again. And now the progression is moving inward, and gravitation is moving outward. And the same holds true in the space region of the cosmic sector, where you have less than 1 unit of time. Then you only have space. He calls it the space region. And again, the progression is now moving inward, and gravitation is moving outward. Okay, so that's kind of the basic framework for him tackling this compressibility problem. Now, this is our 5th episode on compressibility, so if you want to start the chapter at the beginning, go back 4 days. If you want to start at the beginning of the book, go back about 3 weeks. Okay, I'll try to fill in the gaps, but there probably will be a lot of them. Just press on. You don't have to get full comprehension here. You're just trying to kind of get the concepts and the way he thinks about these things. And, you know, this is a lifelong study, but it's worth it, because the stuff that he goes through here in the book on chemistry, much of it can be applied when you study any other subject. And much of it can be applied even if you create your own subjects. You know, I'm a historian. I'd like to create something that you would call reciprocal history, or reciprocal religion, reciprocal nutrition, and so on. But this is reciprocal chemistry. Basic properties of matter, he calls it. Helium and neon, the first two of the inert gases, the elements that have no effective rotation in the electric dimension. Okay, those three number grouping of the periodic table. The third number is the 1-dimensional rotation, Larson refers to that as electric. He refers to the two-dimensional rotations as magnetic. And in the noble gases, that number in the electric rotation is 0. It can be, the third number can be positive or negative. The first two numbers have to be positive, and the first two numbers alternate. So, you know, you get 1, and then you get 1, 1, and then you get 2, 1, and then you get 2, 2, then you get 3, 2, and so on. So helium and neon, the first two of the inert gases, the elements have no effective rotation in the electric dimension. Take the absolute minimum compression factors. Compression is, he's talking about compression from the progression of the natural reference system, which is inward in the time region. So he's referring to an internal pressure, an already existing or intrinsic pressure of these atoms because of the progression. So because gravitation is pulling the atoms away from each other in the time region, and the progression is moving them closer together. So the progression is actually creating this internal pressure, which it has to be added to any type of external pressure that might come from, you know, unrelated independent forces. Okay, so the elements that have no effective electric rotation take the absolute minimum compression factors, because this compression is only in 2 dimensions out of 3, and so it depends on the orientation of the atom, depending on which, how it's oriented, how it's going to be compressed, how much kind of surface against which it's being pressed is effective. So the effective unit of displacement in each of the 2 effective dimensions, the AZY factors, which are the 3 numbers that he's using for this compression chapter, which are closely related to the 3 numbers of the periodic table. The AZY factors for these elements can be expressed as 1, 1, 1. That's the minimum. You always have to have 1. That's the progression. The progression is always there. So, 1, 1, 1 is the rolling back of that progression, basically. The AZY factors for these elements can be expressed as 1, 1, 1. In this notation, which we will use for convenience in the subsequent discussion, the numerical values of the compression factors are given in the same order as in the equations. It should be noted that the absolute minimum compression, that applicable to the elements of least displacement, is explicitly defined by the factors 1, 1, 1. The value of the factor A increases in the higher members of the inert gas series because of their greater magnetic displacement. So you can see that the factor A is related to the magnetic displacement. Because of their negative displacement in the electric dimension, which in this context is equivalent to the 0 displacement of the inert gases, the electronegative elements, those on the right side of the periodic table, just before the inert gases, the electronegative elements follow the inert gas pattern, taking the minimum 1, 1, 1 factors in the lowest members of the lowest rotational groups, and values that are higher but still generally well below those of the corresponding electropositive elements, as the displacement increases in either or both of the atomic rotations. None of the elements of the electronegative divisions below electric displacement 7 has the 4-8 factors, 4-8 AZ factors, the first 2 numbers initially, although they are capable of those high levels and can eventually reach them under appropriate conditions. So those are the maximum numbers that you can get, A, Z, for the first two numbers, 4 and 8. And those have to do with the number of powers. That's 2 to the second power and 2 to the third power, more or less. He did explain this, I believe, yesterday or the day before. All of the electropositive elements studied by Bridgman have the full 4 units in one dimension, that is A equals 4. The value of Z for the alkali metals is equal to the electric displacement, 1 unit. And since Y takes the minimum value under low pressure conditions, the compression factors for these elements are 4, 1, 1 for the alkali metals. That is one above the inert gas, starting with lithium, sodium, potassium. The displacement 2 elements, calcium, etc., take the intermediate values of 421 or 431. The greater displacements of the elements that follow have a double effect. They increase the internal pressure directly by enlarging the effective cross-section, and this higher internal pressure then has the same effect as a greater external pressure in causing a further increase in the compression factors. Most of these elements therefore utilize the full displacements of the active cross-section dimensions from the start of compression, that is 4, 4, 1, where AZ equals AB, the 2 magnetic dimensions, in some of the lower group elements and the transition elements of group 4A, and 481 or 48N when you're talking about using the electric dimension as one of those first 2 numbers. Now, it could seem as if, like, so if Larson's using this equation here, which is like AZY over 938.67, which is the interregional ratio times 6, which he went through the other day. This can seem very much like a fudge factor. Like, well, each one of these elements kind of has its own rotational values that you use, and you're just kind of fitting this in to fit the data of the scientific tables. I think you can definitely accuse him of that. Well, you peaked at the scientific tables and you saw that the compressibility of lithium was X. And so you're setting up these numbers so that you can get a reading that is similar to what X is. I think that's a valid criticism, but I don't think it works because it's not precise enough to kind of get within 1% of his of the number that he's shooting for. Even if he knows the number he's shooting for, he would have to adjust it on a much more fine. It would have to be more finely tuned, I think, to be able to make those kind of adjustments to get it to within like 1%. Now, also, I believe that he applies these things very consistently. Like, once he determines that, okay, the elements in group valence 2 or whatever, displacement 2, electric rotation 2, that they take the 421 or 431 numbers, he applies it consistently through the whole group. So I I don't think he's fudging the numbers here, but it's certainly, you know, a reader who's critical could make that claim, and I think it would be valid. But I just don't think that would be. This isn't enough of a fudge factor to make it actually work. This is just for him to be clarifying the situation. But there are a lot of things like that in this book, where it's like, well, you've created so many different categories that you probably peeked at the numbers and looked at what you were shooting for, and then tried to design the equations to fit the numbers. But I don't think he's doing that. But I could be wrong. Okay, we'll try to maybe read one more paragraph here. The factors that determine the internal pressures of compounds that have been investigated thus far fall mainly in the intermediate range between 411 and 441. NaCl, for instance, has, so now he's moving to compounds. NaCl, for instance, has a 421 initially and shifts to 431 in the pressure range between 30 and 50 megakilograms per square centimeter. AgCl, I guess that's silver chloride, has 431 initially and carries these factors up to a transition point near Bridgman's pressure limit of 100 million kilograms per square centimeter. CaF2 has the factors 441 from the start of the compression. So again, this is kind of like another fudge factor. As the compression goes up, the compression factors also go up. But he does apply this consistently. So the initial values of the internal pressure of most of the inorganic compounds examined in this investigation are based on one or another of these patterns. So he just does have a kind of a finite number of patterns that he's going with. He's not just using any old thing to obtain these numbers. And I don't believe that his fudge factors are finely tuned enough to get him to where he wants to go anyway, in terms of like getting in within 1% of the values. Okay, those of the organic compounds are mainly 411 or 421, or an intermediate value 4.1.5. Okay, we're going to stop there, and we'll take over tomorrow. Just hang in there. This is tough stuff, but it's going to be worth it. All right.